now that you've mastered the electron configuration, let's master the orbital diagram. It's kind of similar, but it has more detail. Sometimes that makes it harder, but sometimes it starts making it easier. By looking at these, we're like, that's what's going on. That's why P can hold 6, but S can only hold 2. And we're going to see a little more detail about it. So it's similar to the electron configuration, but in the electron configuration, I just write the orbital designation and I consider all the orbitals of that type of designation. In the orbital diagram, I draw a line for every single orbital that exists. So what is different is which orbitals have the electrons. I also can see the spin value of each electron. So in some sense, in an orbital diagram, I am showing you not just N and L and a quantity, I'm showing you all 4 quantum numbers for each of the electrons. We'll use a line to represent every orbital with the orbital designation below it, so I know what type of orbital it is. And I'll use an arrow to actually designate the electron in the orbital. If it's an up arrow, we call that spin up, and that means it has a ms value of +1/2. If it's a down arrow, we talk about spin down, or a ms value of -1/2. So it's going to look like this. I would still need to list out from lowest to highest energy all the orbitals, but now I'm going to show each individual orbital. As we've talked about, when I see the p orbitals, p means that there's 3 different quantities, and it's related to the fact that for p, it's a different L value, it's an L value of 1. There are 3 different ML possible values. That's why I get 3. Every time I get to a D, I show 5 boxes or 5 lines. That's because D represents L of 2. So that means -2, -1, 0, +1, +2 for all the possible ML values. That's why I have to have 5 boxes. For F, if we were there, we'd have 7 boxes because there's 7 possibilities for ML. And so I put them in the same order as we did for the electron configuration. It's just the number of boxes changes based off of that letter. Also, this is where Hund's rule comes into place. Remember, Hund's rule says, if you have more than one orbital of the same energy, so we're talking about this set of 3 2p orbitals, or this set of 3 3p orbitals, or this set of 5 3d orbitals. They're all at the same energy. They're all the same designation. In that case, I will put electrons of parallel spin in separate orbitals before I put a second electron in the first one. So it basically means put one in each one before you put the second arrow in there. Let me show you what I mean. It might be easier. So iron has 26 electrons, because if we're talking about the atom of iron, there are 26 protons, 26 electrons. So I can only fit 2, one up arrow and one down arrow in the first box. Since there's only one of that type, I can go ahead and fill it. The next 2 go in the 2s. When I go to the 2p orbital, I put 1 up in the first one, then 1 up in the second one, then 1 up in the third one. Now that each one has 1 arrow of the same spin, they're all going in the same direction, now I can put a second arrow in the first one, a second arrow in the second one, and a second arrow in the third one. That concept of how we fill a P or a D or an F level is called Hund's rule. That's what it's referring to. And it won't make a difference if you do it wrong on the ones that are completely filled, but if you do it wrong on a partially filled one, you will get the wrong orbital diagram and the wrong answer. So the 3s would have 2, so note that I'm up to 2, 4, 6, 8, 10, 12. 13, 14, 15, remember they're all 1 at 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Now that they each have 1, I can put the 26th electron in the first one. So I have 4 unpaired spins, 4 unpaired electrons, where those spins don't have anything going in the opposite direction. So I have, but all 5 of them have some electrons in them, at least 1 electron in them. So you want to be able to do this for all the for all of the elements. These we usually don't go quite up as high as we do on the electron configurations because they're a little bit more complex. It will take a little while, but once you do 5 or 6 of them, you start to get the habit, and it's not that hard. Again, reminding you about this Hund's rule, this concept of these degenerate, meaning the same energy. So when I have multiple lines and they're all the same orbital designation, those are degenerate because they have the same energy. And we will fill them separately with parallel spins. And remember that one's considered ms plus 1, one's considered ms negative 1/2. I'm sorry, ms plus 1/2 or negative 1/2. Okay, now that we've seen this all, let's go back to the periodic table and look at the patterns. We talk about the first two groups as being the S block, group 1 and group 2, and note that there's two of them in a section together, and those are going to represent the orbital designation of those S designations. Over here on the far right is the P's. So remember, I'd do 1s, and I'd fill 1s, and then I'd fill 2s. The next one is 2p. Those show up over here. So the right side of the table that's got a lot of the nonmetals is the P block. And remember, for the P block, there are 3 orbitals, each holding 2 for a total of 6 electrons. So I have a block of 6 groups. Groups 13 through 18 are the P block. Other than period 1, that very first 1s it kind of breaks the habit. Helium is really in the S block, even though it doesn't appear to be. As I move down, then I get to all this transition metal ion atoms. They're the D block. Remember, the D, there's 5 orbitals, each holds 2, that's 10. So groups 3 through 12 are the D block. And then down here, the series, the lanthanide and actinide series, are the F block. If I read the table in order of increasing atomic number, if I know what these are, note that as I go down the table, I increase in N value. So this is the 1s, this is the 2s and the 2p, and the 3s and the 3p. And at this point, you're like, oh, I got it. The number in front is just the period number. It breaks in period 4. The S is the same number, N number, as the period. So it's 4s, 5s, 6s, 7s. But for D, note that it's 1 below. This is the 3D. So it's 1 less than the period. So if I'm in period 4, it's the 3D. If I'm in period 5, it's the 4D, etc. And same thing for the F, except that it's 2 below. If I follow this back to the lanthanide series, this is in period 6, but it's the 4F level, so it's 2 below. But from this is how I can remember the ordering of all the energies of the orbitals. So it's 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s, then 4d, then 5p, then 6s, then 4f, then 5d. So it's kind of built into there to the patterns. Not everybody sees this pattern. Some people really struggle seeing this. It's okay. But if you do see this pattern, it helps to reveal a lot of the structure of the periodic table. Additionally, when I ask you, what is the electron configuration of this element sitting right here in group 14 and period 3, I know that the very end part of it is going to be 3p2 because it's the second seat over in the 3p block. So I know that it's going to be whatever the noble gas is here, which is neon, 3s2, 3p2. So using that noble gas abbreviation works very well when I understand the blocks of the periodic table. I encourage you to use it. You at least need to tell me what these blocks are, that this is the S block, this is the D block, this is the P block, this is the F block. I expect you to know that. I may ask you that on a test. It's even better if you really understand exactly which orbital designation every element is, and you can use that and correlate that to an electron configuration. But some students really struggle with that. If that's the case, you'll be fine with that. Practice drawing some orbital diagrams for selenium and try one for a cation. Try one for zirconium +2 cation.